All right. 2.1 derivative functions. Derivative for a function y equals f of x is the slope of the tangent to the graph of f of x at x and the instantaneous rate of change of y with respect to x. So derivative of a function f of x at a point x equals a, which we have done in chapter 1, right? So we took a derivative for any arbitrary value of a, and we said that that is equal to f of a equals limit of f of a plus h minus f of a over h as h approaches 0. Now we are gonna instead of a using a for arbitrary value, we are gonna use x now. Okay, it is the same idea. So we are gonna do f of x plus h minus f of x over h as the limit as h approaches 0. Okay. So when we took the derivative function, so we use this notation f prime of x. Okay, there is different notations. I'm going to show you all of them. So one is f prime, so that means derivative function. We have Leibniz notation. So this is dy by dx. This is not dy divided by dx, but it is read as dy by dx. This means you are taking the derivative of y respect to x, respect to variable x. This is what it means. So f prime and dy by dx means the same thing, derivative function. We also use another notation, y prime. Okay, that means the same thing, derivative function. Also, with the Leibniz notation, this could be used. Let's say if you have y equals x squared, okay, so derivative function could be written as d of dx squared by dx. Okay, so as you see, instead of y here, dy by dx, we are replacing y by x squared because the function is x squared here. So basically, if you have y equals x squared, if you did all of these limits and find the derivative function, so the final, as a final, you can write it as f prime of x equals 2x, or y prime is 2x, or dy by dx equals 2x, or you can write it this way. So all of them mean the same thing, okay? So the derivative of x squared with respect to x is 2x. So with chapter 2, we are going to look at the shortcuts when we are taking derivative. But 2.1 is doing the derivative using the first principle. So when we use the limit to determine the derivative, it is called the derivative from the first principle. Okay, again, when you are using this limit, when you are doing the derivative, that means it is from the first principle. Okay, if the question is asking you take the derivative using the principle, then you use the limit. If it doesn't say use the first principle, we are going to learn shortcuts later on with this unit. So you will use the shortcuts, not necessary to take the limit. So again, what do we mean with the derivative function? Derivative function tells you the slopes of all the tangents to the graph of f of x. Okay, or the instantaneous rate of change, all the instantaneous rate of change of y with respect to x. Finding the derivative for a number of particular x values using the definition, which is this, would take lots of time. So if you do it, let's say for x equals 2, for x equals 3, for x equals 5, so you have to repeat this process so many times. But if we get the derivative function f prime of x at an arbitrary value of x, then we can use the result to determine the derivatives of a number of particular x values easily. So you do it once for our arbitrary value. Now, when you have the derivative function, so you can just substitute any x value in the derivative function to find the slope of any tangent or instantaneous rate of change at any x value. So with chapter 1, we were doing this with A. We already did several examples. Now we're going to do it with X, but the same idea is there. So let's look at some examples. Example 1. Determine the derivative of f of x equals 3x squared plus 2x at an arbitrary value of x. So we have f of x equals 3x squared plus 2x. So we are going to take the derivative f prime. So the formula goes limit as h approaches 0, f of x plus h minus f of x over h. So I'm going to do f of x plus h on the side. So 3 times sub x plus h for x in a function. X plus 3 times x plus h squared plus 2 times x plus h. So 3 x squared plus 2xh plus h squared plus, let's expand this bracket, 2x plus 2h. Now expand this one, distribute 3x squared plus 6xh plus 3h squared plus 2x plus 2h. Okay, so derivative limit as h approaches 0, f of x plus h is 3x squared plus 6xh plus 3h squared plus 2x plus 2h minus f of x is here 3x squared plus 2x. Make sure you use bracket because you will have to distribute that negative sign in the bracket. Okay, so let's do that. So 3x squared plus 6xh plus 3h squared plus 2x plus 2h. So minus 3x squared minus 2x. Now when you look at it, as you see, 3x squared, negative 3x squared, and 2x, negative 2x are gone. So we have 6xh plus 3h squared plus 2h over h. So as you see, h is factorable in numerator, and that's what you are supposed to have anyway, because as you see, right from the beginning, you have 0 over 0 station, and you need to get rid of it, right? So therefore, h should be factorable in numerator here, so that you can remove this h from the denominator. Okay, so if you didn't get h factorable here, means you made a mistake on the way as you solve this question. So limit as h approaches 0, factor h 6x plus 3h plus 2 over h. H and h is gone. As you do that, again, you removed 0 over 0 situation. Now we can substitute a 0 for h, and you get 6x plus 2. So now you have f prime or derivative function. This means, again, you can find the slope of any tangent by just substituting any x value in the derivative function. So let's look at part B. It says determine the slopes of the tangent to f of x at x equals -1, 0, and 2. So we're just going to take those x values and sub in the derivative function to find the slopes of the tangents at those x values. So B, so we want to find the slope at x equals -1. So we sub -1. So -6 plus 2 gives you -4. So you want to find the slope of the tangent at x equals 0. So you sub 0 in the derivative function. You get 2. So this is slope of the tangent at x equals 0. So find the slope at x equals 2. Sub 2, 12, 40. Next question is asking, determine the equation of the tangent at x equals 2. So we already found the slope at x equals 2. Okay, so that is f prime of 2, which said it is 40. So we're going to write the equation of the tangent, y equals 14x plus b. To find the b value, so we need a point. So that point is going to be point of tangency. So x value is 2. Now you need to calculate the y coordinate of that point. So you need to substitute 2 in the original f of x to get the y coordinate of it. Okay, so f of 2. So let's calculate f of 2 here. Three times 2 square plus 2 times 2, 4, 12, 16. Okay, so that point is 2 and 16. Let's sub in. So 16 equals 14 times 2 is 28 plus b. So it looks like b is -12. So y equals 14x minus 12 is the equation of the tangent at x equals 2. Now, next question is asking you to determine the equation of the line that is perpendicular to the tangent at x equals 2 and that intersects it at the point of tangency. Let's try to figure this out to see what the question is really asking. So I'm going to sketch this function here quickly. Okay. So original question is f of x equals 3x squared plus 2x. So if you factor x here, you get 3x plus 2. Okay. So then the x-intercepts of this parabola is 0 and -2/3. Okay. So -2/3 and 0, and this parabola opens up. Okay, so far what did we find here? We found the slope at x equals -1, slope of the tangent at x equals -1. So let's say -1 is somewhere here. Okay, so I need to make it a little bit closer. So slope of the tangent here, we draw the tangent. Okay, so slope of the tangent, we got -4. So we also found the slope of the tangent at x equals 0. So if you draw a tangent at x equals 0, the slope of this is 2. So we also found the slope of the tangent at x equals 2. Okay, so let's say the x coordinate of it is 2. We got y coordinate being 16. Okay, so slope of this tangent is 14. As a matter of fact, we also found the equation of that tangent. We said it is 14x minus 12, right? So the equation of that tangent is y equals 14x minus 12. So the next question is asking you, okay, part D, find the equation of the perpendicular line at point of tangency where x equals 2. Okay, so we need a perpendicular line to this tangent. They make 90 degrees. So we want to know the equation of this line, perpendicular line. So let's remember, right? If you have a slope of 14, the slope of the perpendicular line is going to be negative reciprocal of that slope. So we know that then the slope of it is going to be negative 1 over 14. But now we need to find what the b value is. Okay, so y equals negative 1 over 14x plus b. So we're going to use a point, and that point is going to be, of course, the point of tangency here. Okay, so point of tangency, x is 2, y is 16. So we're going to solve the same point. So 16 equals negative, so sub 2, negative 1 over 7 plus b. So b is 16 plus 1 over 7. So you can't see. To add them up, so you get 113 over 7. Okay, so then the p value is 113 over 7. So that is the equation of the line that is perpendicular to the tangent at the point of tangency. So those perpendicular lines are called the normal. Okay, so this now normal to the tangent at point of tangency. Let's look at example 2. Okay, so we are going to talk about the existence of derivatives. A function is differentiable at point A if f prime of A exists. So at points where f of x is not differentiable, then the derivative does not exist. So now we're going to talk about 3 common ways for a derivative to fail. So again, if derivative fails, means that the function is not differentiable at those specific points. Okay, now we're going to compare the upper functions where they are differentiable at x equals 0, or xo, okay? And the lower functions here, so upper functions are differentiable at xo, but the lower functions are not differentiable at xo. We're going to compare these two, okay? So one is, as you see, when you look at this, it is continuous, and the function is, there's a continuity at xo, okay? But when you look at the lower function, we see discontinuity. So remember, when you are taking the derivative, you look at the when you are taking the limit. So for limit to be exist, so left side limit should be equal to right side limit. So in this case, as you see, the left side limit is not equal to right side limit. Oh, therefore, there is no derivative at xo. So means the function is not differentiable at xo. So one way for derivative to fail is discontinuity. So let's look at the second way. So as you see, upper function is smooth at xo, but when you look at the lower function, it has a sharp corner, okay? Sharp corner. So therefore, f of x is not differentiable at xo, because remember, when you're taking the derivative, you're looking at the slope of the tangent. But when there's a sharp corner here, how are you going to draw the tangent? Okay, so is it going to be this way? Is it going to be that way? Right? So, but if it is smooth, there's only one way of drawing the tangent. So when there's, again, sharp corner at those points, the function is not differentiable. One of the functions that you know that has sharp corner, probably you will remember, is absolute value functions. Absolute value functions are, there's a sharp corner at vertex. So absolute value functions are not differentiable at those points. So we call those sharp corners cusp. So let's look at the third way, okay? So as you see, so we have this upper function. So tangent is drawn, it has a certain slope. Okay, when you look at the lower function, if you draw a tangent at xo, so that is a vertical line. So vertical lines has, slope. Their slope is undefined, right? So therefore, it doesn't have a certain slope. So the slope of the tangent is undefined. Therefore, the function is not differentiable at xo. Okay, so let's look at example 2. And it says state all x values where function is not differentiable. I'm going to put arrows here. Okay, so when we go from left to right, okay, so we look at -2 first. So -2, we see a sharp corner, cusp. Therefore, function is not differentiable at -2 because there is cusp. So look at -1. It's not differentiable because there's a discontinuity. So let's look at 0. It's not differentiable. Again, there is a discontinuity. X equals 1. We see a sharp corner, not differentiable at 1. 2, as you see, you don't see, but you know that there's going to be asymptote here, right? So again, there's a discontinuity when there's a vertical asymptote. The function is not differentiable there. Also at 3, there's a discontinuity. There's a vertical asymptote, not differentiable at 3, and that's all. Let's look at the last example here. It says find the equation of the tangent and the normal for y equals square root of 2x minus 1 at point x equals 5. Okay, So in the previous question, I talked about the normal. So normal is going to be perpendicular to the tangent, and they're going to intersect at a point of tangency. Example 3, we have y equals square root of 2x minus 1. And we're going to look at the equation of tangent and normal at x equals 5. So to find the slope of the tangent, first we need the slope of the tangent. To get the slope of the tangent, we're going to now use the derivative function to do that. Okay, so then we do y prime. The limit as h approaches 0, so we need to have f of x plus h minus f of x over h. I'm going to do f of x plus h on the side, square root of 2 times x plus h minus 1, so square root of 2x plus 2h minus 1. And f of x is right there, square root of 2x minus 1. Okay, so let's put it here. So square root of 2x plus 2h minus 1 minus f of x is square root of 2x minus 1. So if you sub 0 now, right, you get 0 over 0. So you need to get rid of this situation. How are we going to do it? We are going to rationalize the numerator. Okay, we are going to multiply it by the conjugate of the numerator. So times, I'm going to do it right here, right away. So 2x plus 2h minus 1 plus square root of 2x minus 1. So limit as h approaches 0, by multiplying with the conjugate, so we created difference of squares. So we get 2x plus 2h minus 1 minus 2x minus 1 over h times square root of 2x plus 2h minus 1 plus square root of 2x minus 1. Okay, so if we expand this, 2x are gone, negative 1, positive 1, so you are distributing that negative sign. That is gone, so you end up with 2h in numerator. And again, you were supposed to have h in there so that you can cancel those h's, so that you remove 0 over 0 situation. Okay, so we have now, if you cancel h, so 2 over square root of 2x plus 2h minus 1 plus square root of 2x minus 1. Now we remove the 0 over 0 situation. We can substitute 0 for h. And as we substitute, we don't use word limit anymore. Please be careful with that. Okay, so when you substitute 0, you get square root of 2x plus 2h. H is 0. One plus square root of 2x minus 1. So you have square root of 2x minus 1 plus square root of 2x minus 1. That gives you 2 times square root of 2x minus 1. So 2 and 2 is gone. So you get 1 over square root of 2x minus 1. That is the derivative function, f prime. Okay. Now we want to know what's the slope at x equals 5. So let's substitute 5 in the derivative function. So 1 over 2 times 5 is 10 minus 1, 9. Square root of 9 is 3. So 1 over 3. So then y equals 1 over 3x plus b is the equation of the tangent. So we need point. So x coordinate is 5. So y coordinate we need to calculate. So we need f of 5. So sub in the original function. 2 times 5 minus 1 gives you 9. Square root of 9 is 3. So 5 and 3. So sub in here. 3 equals 5 over 3 plus b. b is 3 minus 5 over 3. So b is 4 over 3. So the equation of the tangent is y equals 1 over 3x plus 4 over 3. So we also need the equation of the normal. So we just look at the slope of the tangent. We take the negative reciprocal. Again, normal and tangent are perpendicular. Negative 3 you will get. And we need the point to sub in to get the b. So we use again the same point of tangency, 5 and 3. So 3 equals negative 15 plus b. And we get 18 here. So y equals negative 3x plus 18 is the equation of the normal.